We'll look at an example of uniform circular motion. So this is a case where an airplane tilts its wings, so it's banking. Just use part of its lift to provide the radial force so that it can execute circular motion. This is, ever been on a flight and you're waiting for your airplane's turn to come in to land, you'll be familiar with this maneuver of just the airplane banking and making a wide turn, waiting for its chance to come in and land. What we're given in the problem is the weight of the airplane, not its mass. So the weight in newtons, its speed is currently 90 meters per second, so that's about 180 miles an hour. And the wings are banked at 20 degrees. We want to find what's the radius of curvature of the plane's circular path. This sort of problem is going to be similar to a banked curve for a racetrack or a velodrome, where part of the normal force in those cases where the object is in contact with the road or the track, it's part of the normal force that's helping create the radial force for making the turn. In this case, it's an airplane up in the air, and so it's a lift from the wings. So I'm going to draw the free body diagram for this particular instant and its turn. And obviously, as it's turning, it's going to face in a different direction. So the velocity vector changes its direction, and the acceleration vector changes its direction. But for uniform circular motion, those are both constant in magnitude. So draw in the wings of the airplane. So those are tilted at 20 degrees. So that's 20 degrees, and that's 20 degrees. The weight of the airplane is going to act straight down. So I put that vector in. So acting from the center of mass of the airplane. And lift acts perpendicular to the wings. So there's the lift vector. So that's a right angle. Now compared to the vertical direction, if this is tilted by 20 degrees, this is also tilted by 20 degrees, and we can see that the lift vector is going to have two components. Part of it is along the y direction, and part of it is along the x direction. Alright, so for our airplane, it's in equilibrium along the y direction, along the vertical direction. So I can say that I add up all of the y components of forces, and Newton's first law, those are going to sum to 0. Writing that out, I'm going to have that the lift L times cosine of 20 degrees to give me the y component of the lift minus the weight equals 0, and move w to the other side. L lift cosine 20 degrees is equal to the weight, or that the lift is the weight of the airplane over cosine 20 degrees. Alright, so we've taken care of the weight in one component of the lift. The x component of the lift is what provides the radial force, so that is causing the radial acceleration for the airplane to change the direction of its motion and go into circular motion. So I add up all of the forces along the radial direction, and that's going to be the mass of the airplane times the radial acceleration. So that's Newton's second law of motion. And at this instant in time for the free body diagram, the radial direction is the same as the x direction. So writing that out, for uniform circular motion, the radial acceleration will be the speed squared over the radius of curvature. And the only force I have to cause that is this component of the lift, the x component. So that's going to be L times sine of 20 degrees. And we had worked out before how big the lift is. So I'm going to go ahead and substitute that in, that the lift is the weight over cosine 20 degrees. So I'm going to have the weight times sine of 20 degrees over cosine 20 degrees. That's going to equal the weight times tangent 20 degrees. All right. So I'm going to go through and solve for the radius of its circular path. So let me get my two bookends for this equation. I've got an mv squared over r is equal to the weight times tangent of 20 degrees. I want to solve that for the radius of its circular path. So that tells me the radius is going to be mass of the airplane v squared over the weight tangent 20 degrees. And I don't actually have the mass, so I'm going to do a little rearranging here. I'm going to multiply the top and the bottom by the acceleration due to gravity. So I'll get the weight in the numerator. So this is going to become v squared over g tangent 20 degrees once I cancel out the weight. So the weight cancels out with m and g. All right. We get here to the very end. I'm going to put in our actual numbers. So the speed, 90 meters per second, and you just square that. The airplane is on Earth, 9.8 meters per second squared, and I have a tangent of 20 degrees, just a pure number. That's going to give me, when I put in my calculator, 2.3 times 10 to the 3 meters, so a little bit over 2 kilometers, which seems pretty realistic for airplanes. The weight was realistic, but that cancels out. Speed of about 180 miles per hour, not an unreasonable speed for an airplane, and then tilting the wings by 20 degrees will give you a radius of curvature of a little over 2 kilometers.